Hello everybody, welcome to my YouTube channel. Today I'm going to talk about 3D reconstruction. So this is a series of video which is part 3, and I have already talked about OpenPose setup and camera calibration, which are part 1 and 2. If you haven't watched those videos, part 1 and part 2, I highly recommend you to watch them, because I'm just gonna directly jump into 3D reconstruction part, and I assume that you have watched those two videos. Okay, so I'm just gonna skip those two parts and go into 3D reconstruction slide, which is right here. So there are three breakpoints I just want to go through in this presentation or in this video. So first one is direct linear transformation. People call it DLT. And I'm gonna apply DLT for camera calibration cache in the OpenPose data. So we have already talked about band adjustment in the previous video, and I didn't really touch in details how you can do this reconstruction on the calibration case. So in this presentation or this video, I can talk more details. And the second breakpoint is filtering, how you can filter the data and optimize the data after 3D reconstruction. So the main point of direct linear transformation is to find out the crossing point between multiple projection lines. So let's say in the simple scenario, you have two cameras from different angles and pointing at the 3D, the point in the 3D. And of course, in the camera plane, you only have like 2D points somewhere in the screen, or camera screen basically. And if you know the 2D point in the projection matrix, you can draw the line through the camera plane, and at some point you will hit the point in 3D. However, if you have only one camera view, you don't know where and when the projection line hits the point in 3D. So that's why you need another camera source pointing at the 3D point in the different angle. And if you draw the two lines, eventually two lines cross, and that's the point in 3D basically. And if you're looking at the crossing point of projection line right here, you can, unless line the parallel, you can find the crossing point. However, in 3D, most of the time that's not happening. So when you turn around the projection line in 3D, oftentimes there's a gap between the lines, and what you have to do is you have to estimate the middle point of two lines, right? So that is the terminology, triangulation and DLT. So you can calculate 3D data out of multiple 2D data. So coming back to the formula again, so 2D point is equal to camera intrinsics times camera extrinsics times 3D point, and camera intrinsics and extrinsics are projection matrix right here. So you can reformat the formula with this. So L1 is the first parameter in the projection matrix right here, and the minus U, which is the x point, times L9, so 9 parameters in this matrix, and you will stack this data for X and Y, and if you have multiple camera views, you will just append or like a stack those data to create one huge matrix. and you will apply SVD, singular value decomposition. So that's the kind of the details like behind how you can calculate or reconstruct 3D data or the calibration case. So if you have OpenPose data, you can do a little bit further, because OpenPose can output confidence rate on top of 2D points. So if you have, for example, like knee data, knee x and knee y, and OpenPose can output how confident this point is, right? And again, you will have to reformat the data, but only difference is you can multiply the confidence rate in each part, so that you can weigh the projection matrix. So again, if you just do normal triangulation, calculating the middle point of two projection lines right here, so here and this gap, and if the one projection matrix has high confidence rate, you can move the middle point a bit towards the stronger line compared to the other lines. So that's how you can weigh the projection lines, and hopefully it will improve the accuracy of 3D data. And again, you just need to do singular value decomposition to extract meaningful data, or like 3D data basically. Alright, so let's jump into Python code. So if you just want to do normal 3D reconstruction, you will just need to have a projection matrix right here, and x point which is u, and y point which is v. So you just need to calculate 4 parts right here for x and 4 parts for y, and I'm not sure like how many cameras you will have, but you will stack those data as many as you have the cameras basically. So in this example, I had 12 cameras, so you will append this data 12 times, and you will create one huge matrix. And you will apply SPD, singular value decomposition, and you will normalize the data, and you get 3D data right here. Alternatively, if you only have projection matrix, it's a 3x4 matrix, and you have 12 parameters, but like you can also use only like 11 parameters, because the last parameter is just like only like a weighting, and you can append the data separately with this 3 parameters for x and y, and you will have this parameter separately, and afterwards you will transpose this matrix and inverse this matrix, and you will have dot product between. Then you will have the same 3D data right here, right? So whichever you prefer, it gives same result. And for the OpenPose data, only difference is just a multiply confidence rate right here, so that you can weigh the projection matrix, and everything else is the same. Okay, so going back to the presentations right here, so next breadpoint is filtering. So there are a bunch of ways you can filter the data, and what I use for this example is residual analysis. So basically, residual is the error between original data and filtered data. And if you use Butterworth, one of the most difficult questions you have to ask yourself is what is the color frequency? So what is the best color frequency? And you can go to the literatures and depend on the situation. You can of course looking at power spectrum to find out what is the noise and what is the data you want to extract, so on and so on. I mean, of course you can do it, but it's time consuming. Instead, what you can do is define the range of color frequency you want to determine. Let's say from 1 to I don't know, 19 or 20 right here, and you will just calculate the residual, which is the error between original data and filtered data, and you will only extract the residuals, which is the error, and you will draw this nice residual curve right here, and x-axis as the color frequency. And as you can imagine, if the color frequency is really really low, you filtered like almost everything. Like you filter noise, you filter the data you want to extract, so the error should be huge right here on the top. Right here. However, if you keep decreasing the color frequency, you will accept the data, and eventually you will accept the noise, so that the error will be minimized and eventually going to the zero, because you will accept everything including errors, and which is original data also has errors inside, so you will get really nice curve after having residuals against the color frequencies. So what I want to have here is the from the tail of the curve, you will calculate the slope, and you will extend it until you hit the y-axis right here, and from the whatever crossing point, you will use a horizontal line right here, and you will find a crossing point between horizontal line in the residual curve. And when you look at x-axis, you will have the appropriate color frequency right here. Right? Want to minimize cutoff frequency, want to minimize the error, so that's the best point. So I will probably just jump into MATLAB and how I do it, but first of all, maybe I'm just gonna explain how you extract the data from the JSON. So after you run in OpenPose, you will get JSON files, and at a human readable data, so you just open it in Notepad or so, and you can see it like data really easy. But how you can extract the data, so basically I'm just gonna access to the folder, like a JSON folder, like I store like all the JSON files and extract on the names, and after that I will just use the file read function from MATLAB, and I just extract the data inside in the string format. And there is another useful function called JSON decode, and I get the data in struct format. So in the struct format, like I can just extract the data using dot function right here. So I can try to automate the process of extracting the data from the JSON. But as you know, OpenPose can detect multiple people, and sometimes there are multiple people in the one single frame, and OpenPose doesn't track any person. So if you have one uh, detection ID or like a person ID in the one frame, and the next frame there is a possibility that the ID is switched or lost or like going somewhere. That's really really possible. So to make sure I'm tracking the right person, I just created this really really long code right here. But the main point is track the person with the error. So how are we going to calculate the error? So error is the human pose estimation data in the previous frame and comparing it with the current frame. So the first slide or the first data point of first frame, I have to select the person to track, right? If it's only one person, it's just automatically going through the process. But if there are multiple people instead of one frame, in the first frame, I have to select one person to track. And keep the pose data, human pose data, and going to the next frame, and let's say having 3 people, and just compare the pose data in the previous frame with those 3 people, and finding out the the person with lowest error, and that's the person to track. And at some point, if there are many people or like the person with error, like the person with minimum error was more than 100 pixel errors, then I will go back to the first process, choosing the right person to track, and then going to the next frame. So it's kind of like a half manual and half automatic way to track the people. So it works good so far. So I just keep this code, and I have to select person sometimes, but I value the accuracy more, so I just keep this code right here. And I have to, after extracting all the data, I have to model the data, which means separating the confidence rate and the XY post data. And I just want to check the data sometimes and clean up the data. So the OpenPose doesn't detect anything. It gives 0. So I have to fill the missing data. I use the linear method, but you can play around. There are so many methods that you can choose, and I just use linear because it works so far good. And smooth the data. So this is the point I use the residual method. So I define the range from 1 to 10, and the steps is 0.1, and I calculate root mean square error right here. This is original data, and this is filtered data, and this is the error variable which I store, and find out the minimum error point, and calculate the slope and the intersect point, and fit in the curve, and finding out where is the cutoff frequency point, and do the filtering. Check the data again and save the data. So that's how I do the data extraction from the JSON and filter the data. Alright, coming back to the presentation slide, and the last breakpoint, which is optimization. So this is actually one of the questions. Before that, actually, filtering method. At this point really not sure when is the best, when, where is the best way to use this actually. So of course you can use this filtering method when you get the pose data from OpenPose. You can use this after 3D reconstruction. There are so many places like you can apply this filtering method, and I still don't know, when, where is the best. So I also have to play around with this filtering method, of course, but also like when, where, which timing you have to do the filtering. So that's it, like one of the questions I wanted to mention right here. And again, optimization, the same concept. I don't know, like if this really optimizes 3D data. I have used this optimization method multiple times in different situations. Sometimes it works, sometimes not. But anyway, I will explain how I did it. So the equation right here stays the same. 2D points is equal to camera intrinsics, extrinsics, and 3D points right here. And use 3D least square method to refine the 3D reconstructed data by minimizing the reprojection error. So what's the reprojection error? So basically when you calculate 3D points by using 2D points and the projection matrix, you will get this x point. And when you do the 3D reconstruction, you can always calculate back to the 2D points using 3D point and the projection matrix right here. However, this 2D point is not always the same as the original 2D point, so there's a gap between. So that's the reprojection error. In this case, I have 2D points from the OpenPose and calculate the 3D points right here. And using reconstructed 3D pose data and the projection matrix in each camera, I can calculate 2D points. Right, and comparing the original 2D points from OpenPose with this reprojected points, we can minimize those errors and refine the 3D reconstructed data. However, this assumes that the point from the OpenPose is the reference, and the projected point has error, so we can minimize. But the thing is, the 2D points from OpenPose is also the estimation, right? And I'm not sure if that's accurate enough. And if it's inaccurate, what is the point of minimizing the error which are from inaccurate data? And yeah, so that's the questions I have to ask myself, and you have to ask yourself as well. And obviously, since we are using 2D points from OpenPose, we can also use the confidence rate to weigh the errors. So, one error is bigger than the another error because of the confidence rate. If you have more confidence with that point, error should be minimum or like smaller compared to the point with low confidence rate, so that you can kind of optimize which point should focus on when you use the least square method. But again, this is a discussion after we find out this is the right way to optimize 3D reconstructed data. And I still don't know, and I have to play around. If you know the answer, please help me. This helps a lot, and I haven't seen this, kind of like optimization method when you do the 3D construction. But it worked in some situation, and it completely lost in like another situation. So I don't know still the answer. But yeah, so this is the last part I'm gonna present in this YouTube video, and if you have any questions, you can leave the comment. I try to answer the questions as quickly as possible, and after this video, I'm gonna prepare kinematic, and kinetic simulations we can do after 3D construction, which is very useful and fun. And I think I'm gonna create two different videos for kinematic and kinetic. So until then, see you. Bye.